Okay, when last we met, we had started talking about electron configurations. Electron configurations show the particular orbitals that electrons occupy for an atom. In other words, it shows the address for every single electron in an atom of an element. When we talk about ground state electron configurations, it means that the electrons fill the lowest energy states first. This is known as the Pauli exclusion principle. Well, no, I'm sorry, that's the off-ball principle. The Pauli exclusion principle is directly related to what we do with electron configurations, though. When we develop an electron configuration, you will notice that each of the lines represents an orbital. And as I've been filling the orbitals, I have put no more than 2 electrons in each orbital. There is a reason for this, and that is because no 2 electrons can have the exact same 4 quantum numbers. And our 4th quantum number is the spin quantum number, and there's actually only 2 options for it, and that's a +1/2 and a -1/2. That is our 2 electrons that can go in any one orbital. When we are putting in the electron configuration or developing the electron configurations, you will notice that when I placed an electron in an orbital, I always did so spin up first. That is just standard notation. We really can't tell whether an electron is spin up or spin down unless we run it through a nuclear magnetic resonance instrument. So it is mainly common notation that we do this with. So when I developed the electron configuration for helium on Tuesday, helium is element number 2. It has 2 electrons. The 2 electrons went into the lowest energy orbital, which was the 1s orbital. One went in spin up, the other went in spin down. We developed the quantum numbers for those 2 electrons. And if you look at the quantum numbers, the N, the L, and the M sub L were all the same. They were 1, 0, 0. The difference between the 2 electrons in helium is that the first one was +1/2 for spin up, and the second one was -1/2 for spin down. Again, that comes back to the fact that no 2 electrons can occupy, or excuse me, that no 2 electrons can have the exact same 4 quantum numbers. Question. Okay. Now, there are 2 other guiding principles that we use in determining the electron configurations. The first is the off-ball principle. And folks, you're not tested over these definitions. You're tested over understanding the concepts. The off-ball principle is the systematic building up of electron configurations by adding electrons so that the energy of the atom is as low as possible. In other words, we add the electrons in the lowest energy level first, and we slowly build up, adding electrons higher and higher in energy. The second principle that we use is Hund's rule. Now, we actually haven't seen Hund's rule in effect yet. Hund's rule says that when you fill degenerate orbitals You place one electron in each orbital before you pair them. Now, Hund's rule comes up with this term of degenerate orbital. So we need to define what a degenerate orbital is. Basically, it is a subshell that has more than one orbital. From our quantum mechanics, what that means is it is an L value that has more than one M sub L. So basically, that's everything but S. If it is a P subshell, L is equal to 1, M sub L is equal to -1, 0, and 1. It has 3 orbitals, therefore those 3 orbitals are degenerate orbitals. So we would put 1 electron in each orbital spin up before pairing. The D subshell. D subshell means that L is equal to 2. If L is equal to 2, then the options of M sub L are -2, -1, 0, 1, and 2. It has 5 orbitals. So the D subshell represents a set of degenerate orbitals. We would put 1 electron in each orbital before we pair them. That's what Hund's rule states. So let's look at carbon. Carbon is element number 6, so its atomic number is 6. So it has 6 protons and it has 6 electrons in a neutral atom of carbon. The first electrons, we put in the 1s and we put it in spin up. Because the 1s is lowest in energy, according to the Aufbau principle, we would then put our second electron in the 1s as well, but this one would be spin down. We would then move to the 2s because it is next lowest in energy. The first electron in the 2s would go in spin up. The second electron in the 2s would go in spin down. So far, we have distributed 4 of the 6 electrons. We then move to the 2p because that's the next lowest in energy. But now we have a set of degenerate orbitals because we have 3 orbitals in the subshell. So we place 1 electron in each orbital spin up before pairing. What we are developing here, folks, you'll sometimes see me write as 1s, 2s, 2p, and I refer to this as the box diagram. And it's referred to as the box diagram because sometimes when you see this, these electrons will be boxed in. But it's referred to as the box diagram, yes.
How can an element like that when one of the orbitals is still empty, does it matter which 2 the electrons go in? Like, if you're finding like the quantum numbers for the last electrons, does it matter if you put like an M sub L of -1 or 0 or 1?
Technically, no, because we're not solving the Schrodinger equation, so we don't know which one it went into. However, to make life easier, a lot of times I will use the box diagram and go, okay, so my options so with a P subshell, that means that L is equal to 1, so my M sub L is equal to a -1, 0, and a 1. I will go ahead and put in here -1, 0, and 1 just to make my life easy. But technically, since we're not solving the Schrodinger equation, we don't know which one it goes into. Now, if you're asked for the basic electron configuration or anything that's kind of the word basic, then what they're asking for is they're asking for you to put the shell, the subshell, and tell me how many electrons are in that subshell. So 1s2, 2s2, 2p2 would be the basic electron configuration. It all means the same thing. The difference is whether we're illustrating the electrons or whether we're just stating how many electrons are in that particular subshell. Now, for the quantum numbers, as was mentioned, the number represents the N value. The letter represents the L value. So when we have an S, that means that L is equal to 0. So our first two electrons would have the number 1, 0. Well, M sub L can be anything from a -0 to a +0. So in other words, it's also 0. And the first electron went in, spin up. So it's a +1/2. Folks, this literally tells me that in the first shell away from the nucleus, I have a spherical subshell. There is only one orbital in that spherical subshell, and my electron is spin up. That's what those quantum numbers tell me, which is the same thing that the electron configuration is telling me. The second electron would be 1, 0, 0, -1/2, because it's in the same shell, same subshell, same orbital. The only difference is it went in spin down. My next two electrons went into the 2s. So my next two electrons would have the shell number of 2. Being an S, it is still an L of 0, which means my M sub L is 0. And again, it goes in spin up. So the third electron in carbon is 2, 0, 0, 1/2. The fourth electron is in the same shell, same subshell, same orbital. So that means the first three quantum numbers are all the same. The difference is the fourth electron went in, spin down, so it's a -1/2. Now the fifth electron went into the 2p. Now p is represented with a 1. And as we were just talking about, technically it could go into any M sub L value, -1, 0, or 1. But to make life easy, it's just easier if you label them in the same order. So this one I would have said was a -1, spin up was a +1/2. The second electron in the p subshell had to go in a different orbital. So if you put the first one in -1, then you've got to put the second one in a different M sub L value. And it also went in spin up. Questions? Let's look at another example. Let's look at neon. Neon is atomic number 10. So it has 10 protons, and in a neutral atom has 10 electrons. We always follow the off-ball principle by placing our electrons in the lowest energy shell and subshell first. So we place them in the 1s before moving to the 2s, and then we move to the 2p. Because the 2p has 3 orbitals in that subshell, they are degenerate. So you place 1 electron in each orbital before pairing them up. The electron configuration is 1s2, 2s2, 2p6. Add up those superscripts, you get 2 plus 2 plus 6 is equal to 10. Now I want to introduce another type of configuration. And this is going to be the noble gas configuration. In the noble gas configuration, there are 2 parts. The first is the last noble gas will be in brackets. Or I should say the prior noble gas will be in brackets. With electrons not in the noble gas being listed next. So what is the noble gas that came before neon? Helium. So we would place the elemental symbol for helium in brackets. What you just did is said, hey, I have everything helium has. Now I just need to list what helium does not have. Helium does not have the 2s2 or the 2p6. So the noble gas configuration for neon is helium, 2s2, 2p6. Now you may go, okay, how do I know this? This is where understanding the periodic table arrangement is important. Because what you've done is you said, okay, I have everything helium has. Now I only need what helium does not have, which starts right here. This is the S block. So it has the 2s2, and it has, this is the P block, and it has 2p6. That's what neon has that helium did not have. Let's look at magnesium. Yes.
Because neon's a noble gas, how come we can't just write neon?
You always go to the noble gas that came before the element when you write the noble gas configuration.
Get that, I was just asking why, if it is a noble gas, why can't we just start with that? Cause it's like, we already, if we're assuming that we already know what every noble gas is, then why can't we just go, oh yeah, that's neon?
And I've debated this one for a long time, but why would the electron configuration of neon just Na be just Na? You've got to have an electron configuration. You got to tell me something about the element. And the main reason is when we get into the noble gas configuration, what we're really seeing is something more about that element's valence electrons, because again, that's what's responsible for the reactivity. So we haven't talked about valence electrons yet, but when we write a noble gas configuration, the majority of valence electrons, or the valence electrons are illustrated in the electron configuration that follows that noble gas symbol. So that's the primary reason. Is because again, why are we learning about electron configurations? What's the main reason for it? To understand an element's reactivity. That's the main reason. And so if you don't write those, the 2s2, 2p6, you're not indicating the valence electrons for the atom, and therefore you're not indicating its reactivity. Think it'll become more clear as we do some more? Okay, magnesium is element 12. So it has 12 protons and 12 electrons. We start the lowest energy, so 1s, and put 2 in there. Then we move to the next lowest, so the 2s2. Then we move to the 2p's, and because they're a set of degenerate orbitals, we place 1 in each orbital before pairing it up. Then we move to the 3s, and we put in 2 electrons, and that gives us 12 electrons. So the electron configuration would be 1s2, 2s2, 2p6, 3s2. The noble gas configuration would be what? Neon. We use neon this time because that is the noble gas that came before the magnesium. By writing the word neon in brackets, we're saying I have everything neon has. I only need to know what neon doesn't have. Well, this is the S block. It's 3s, and there are 2 electrons. So the 3s2 is what neon does not have. I could write a box diagram. Now, I will be honest, once I get into this, I usually start, instead of writing a line for every single thing, I could go, okay, that's 1s, 2s, 2p, 3s. But you'll also see me start to go, okay, I'm going to use the noble gas configuration and just show the 3s as the box diagram. Either one of those is acceptable, but again, a lot of this is about those valence electrons. A lot of it is about the electrons that are responsible for the element's reactivity. So that's why it is perfectly acceptable to write a noble gas box diagram, is because again, you're trying to focus on the element's reactivity. Yes.
For the noble gas configuration of like helium or hydrogen.
Helium and hydrogen, I never write the noble gas configuration because there's not a noble gas that came before hydrogen or helium. You can only do it for elements after helium. Now I'll give you a heads up on how I do things on an exam. You will be asked to write multiple electron configurations. But for the basic electron configuration, which can get quite tedious, which I will show you, I usually stop at calcium. I require noble gas configurations for the elements after calcium on a test. And that is simply because I'm trying to reduce how much writing you have to do. And yet test you on both concepts. Okay. Most of the time, you're not going to have the energy diagram that I've been giving you. You have to be able to determine things directly from the periodic table because you're given the periodic table on every exam. So you have to know this breakdown. That it is the 1s with helium being a 1s. Then the 2s, 2p, 3s, 3p, 4s, 3d. Again, we put the 4s before the 3d because it's just slightly lower in energy. And then we move to the 4p. 5s, 4d, 5p, 6s, 4f, 5d, 6p, 7s, 5f, 6d, 7p. You have, but folks, the reason the periodic table is arranged this way is already because it takes into account that energy diagram. It takes into account those energy levels. But it also, so we know it takes into account the principal quantum number. It takes into account the angular momentum quantum number, but also embedded in that periodic table to some degree is the magnetic quantum number. How many orbitals can an S subshell have? 1. How many electrons can go into an orbital? 2. That is why the S subshell is only 2, or the S block is only 2 elements across. How many orbitals are in the P subshell? 3. How many electrons can go into each orbital? 2. 3 times 2 is 6. That's why this block is 6 elements across. So it's telling you how many lines. If you were asked to do the box diagram, all you got to do is count the number of elements across and divide by 2. So how many orbitals are in the D subshell? 5, because it's 10 elements across. How many are in the F subshell? 7, because it's 14 elements across. Okay, so let's develop the electron configuration, the box diagram for our, yes.
57 and 89, are we gonna get those because you said like, we don't know which ones they belong to?
Normally, I avoid 57 and 89. Just because, I mean, they technically do belong to the D subshell like it shows on that periodic table, but I just avoid them because it is dependent upon which periodic table you're looking at as to what makes sense. So, okay, argon. You start at the beginning with the 1s, and it is 2 elements across. Then we go to the 2s, and it is 2 elements across. Then we go to the 2p, and it is 6 elements across. Then we go to the 3s, and it is 2 elements across. Then we go to the 3p, and argon is the 6th element in that. So its electron configuration is 1s2, 2s2, 2p6, 3s2, 3p6. What noble gas came before argon? Neon. By writing neon, you've just included everything neon has. You only need to include what neon does not have. So we have taken care of everything in row 1 and row 2. We only need to start with the 3 S's and then go to the 3 P's. So its noble gas configuration is neon 3s2, 3p6. Let's look at zinc. Zinc is element number 30. We start at the top. If we're writing the basic electron configuration, 1s2. Then we move to the next one, 2s2. Move over to the right, 2p6. Then we move to the 3s, 3s2. Then we move over to the right, 3p6. Then the 4s's. And then the 3ds. Again, the D, to figure out that it's 3D, it is going to be the period minus 1 is equal to your N value. And therefore it is, and zinc is the 10th element in the 3Ds. To write the noble gas configuration, what noble gas came before zinc? Argon. So we're placing argon in brackets. That means that we just took care of row 1, row 2, and row 3. We don't need to worry about those. We only need to include what starts with row 4, which is the 4s2 3d10. Questions? It will come back up in a moment. But before I talk about the anomalies, I want to talk about the elements. If I write the noble gas configuration for lithium, it is helium 2s1. If I write the noble gas configuration for sodium, it is neon 3s1. If I write the noble gas configuration for potassium, it is argon 3s1. Oh, excuse me, 4s1. I can continue. If I write the electron configuration for fluorine, it is going to be helium 2s1 2p5. If I write the electron configuration for chlorine, it is going to be neon 3s2 3p5. If I write the electron configuration for bromine, it's going to be argon 4s2 3d10 4p5. What you will notice is that the electrons in the highest shell is equivalent for all elements in a group. Now, it may not be as obvious on the bromine, but again, the shell is represented by the number preceding a letter. And in the 4s and the 4p, there are 7. Why is this important? Well, comes back to the story we started. We said that the original philosophers arranged that periodic table first, yes, based off of atomic number. Second, they noticed that every so often the properties repeated. And therefore, those elements whose properties repeated wound up in the same group. The reason those elements' properties are similar to each other that are in a group is because they have the same number of electrons in that outermost shell. And that is true for all of your main group elements. Now, your transition metals, they behave differently to some degree, but your main group elements, this is the story. This is what was observed. Questions? Now, anomalies. There are are anomalies scattered throughout the entire periodic table, but there are two groups whose elements are all anomalies and they all behave the same. They are group 6 and group 11. Because the S subshell and the D subshell are very close in energy, it is foreseeable that an electron can be promoted from the S subshell into the D subshell because it wouldn't require that much energy to do so. And in fact, in group 6 and group 11, that is exactly what we observe is an electron in the S subshell is promoted into the D subshell. This promotion occurs to obtain a degree of stability because two half-filled shells are more stable than a full shell and a partially filled shell. Or a half-filled and a full shell are more stable than a full shell and a partially filled. In other words, if I can get a half-filled or a full shell by promoting one electron, that's going to be better than a partial. And that's exactly what occurs. Is we wind up promoting an electron. So let's look at an example. If I were to write out the noble gas configuration of chromium, I would get argon. And I were to write it per normal, I would get argon, 4s2, 3d4. But by allowing the 4s electron to be promoted into the 3d, I wind up with two half-filled subshells. This is more stable. And therefore, the electron configuration for chromium is going to be argon 4s1, 3d5. Again, this is going to occur with group 6.
On the exam, are we gonna be asked to show like the first one and then the change too?
You don't have to show the change. You have to show what it actually is. So I am just explaining why it's going the route, but you don't have to illustrate it on the test. But you have to get the correct electron configuration, which is this latter piece.
It's more stable that way because all the orbitals get filled.
It's more stable because all of them are half filled. So we don't have any basically, when you put in that first electron, there's energy involved. When you spin pair it, it actually increases slightly in energy. So this version is slightly, because of that spin pair, is slightly higher in energy. And I'm talking real slight, but it's there. Whereas this winds up being a lower in energy because all of the electrons are spin up. They're all unpaired. Once you pair an electron, it increases the energy ever so slightly.
On this row six and eleven will have the same configuration as the one to the right.
Not the exact same because they don't have a full S. Not the exact same because they don't have a full S. Let's look at silver. Silver is going to be argon. No, it's going to be krypton. 5s1. Well, if we were to fill it normally, we would want to go, okay, 5s, 4d, and we would obtain this. But by promoting that electron, I mean, it's already spin down. And if we promote it into the 4d, what we wind up with is we wind up with a half filled and a full subshell, which provides stability. So this one is more stable. So for group 11, you're going to promote an electron from the S subshell into the D subshell so that you have a half-filled S and a full D. Questions? Yes. These are the only ones you have to memorize. And the only reason I have you memorize these is because pretty much every element in that particular group does the exact same thing. Whereas, and what we observe is the anomalies tend to increase the further down we go in the periodic table, simply because once you start getting to these bigger atoms, the nucleus really doesn't care what's going on with the electrons as much. Whereas when you've got a really small atom, the nucleus fills every single electron. Okay, earlier, before the anomalies, I showed you this slide. Well, we have a term for these electrons. That term is valence electrons. They are the most important part to bonding. We are going to talk about those valence electrons a lot. Because when we start building Lewis structures, we're going to build them with the valence electron. The valence electrons are responsible for the bonds that the elements form. So we're going to talk about those valence electrons a lot. Again, like I showed you on bromine, they are the electrons in the outermost or the highest in value. So I only took into account the 4s and the 4p. Excuse me, the 5, no, yeah, the 5, for bromine, I only took into account the 4s and the 4p, yes. Now, the next two lines give you an easy way to determine the number of valence electrons. For the main group elements, just look at the last digit of its group number. I gave you lithium, sodium, and potassium. They all had one valence electron. They're in group 1. The last digit is a 1. For fluorine, and bromine, I said they had 7 valence electrons. They're in group 17. The last digit is a 7. They have 7 valence electrons. Guess how many valence electrons carbon has? 4, because it's in group 14, the last digit is 4. Guess how many valence electrons neon, argon, krypton have? 8. We're going to use that, folks. That's going to be called an octet, and it's going to be extremely important. Now, helium is the oddball. Helium doesn't follow that rule, but for all the rest of the main group elements, you can look at the last digit of the group number, and that will be how many valence electrons it has. If it's not a valence electron, that means it's a core electron. Now, I talked about the main group elements. What about the transition metals? Well, for your transition metal, oh, I deleted it. If you look back at zinc, you will see that in the highest shell, there were the 4s2. If I had have done nickel, there would have been 2. The 4s2. If I were to do ruthenium, there would be 2. The 5s2. Except for your anomalies, the most common, or except for your anomalies, the number of valence electrons is 2 for all transition metals. The anomalies, there is only 1. So, yes, you'll have something like this question on the test. Somebody give me a number that is the number for nitrogen. 5. 5. Group 15, last digit of 5. 7. Group 17, the last digit of 7. 2. Group 2, the last digit of 2. 1, because it's in group 11, which is an anomaly. 2, because it's a transition metal that is not an anomaly. That, folks, should be easy points. Should be quick to click off. We talked about the ground state compared to the excited state. The ground state means that the electron is going to fill into the shell and subshell closest to the nucleus because it's lower in energy. So for hydrogen, that 1 electron of hydrogen goes into the 1s right next to the nucleus. Anything else would be an excited state. Here's an example of carbon. We did carbon earlier, 1s2, 2s2, 2p2. But if I take that electron in the 2s and I promote it to the 2p, because it's not one of my anomalies. It's not one of the anomalies. If I promote that electron to the 2p, now I'm in an excited state. So ground state just means that the electrons fill according to the Aufbau principle excited state, except for the anomaly. Means that the electrons are in a electron configuration other than what you expected. So again, excited state follows Aufbau principle. I'm sorry, ground state follows Aufbau principle. Excited state means that they are not in what is expected of them. So let's look at an example. First of all, add up the electrons. That is the first thing you should do. I have 2 plus 2 is 4 plus 6 is 10 plus 1 is 11 plus 1 is 12. What element is it? Magnesium. And what would you expect magnesium's electron configuration, noble gas configuration to end with? 3s2. This is its ground state. This is an excited state. Because the electrons didn't fill the way you expected them to. They're both the same element. Just one is excited and one is ground. Yes.
It says one or more electrons, is that like more than one electron each of them?
Oh, yes. We did helium, but I mean hydrogen the other day, but we could have done helium and had more than one electron that was excited at a time. So yes. It just means that the electron configuration is not as expected. The last thing I wanted to quickly do is diamagnetic and paramagnetic. Even though paramagnetic means that you've got electrons unpaired. Di means 2. Diamagnetic means that all electrons are paired. I know that's the paramagnetic is kind of counterintuitive because you think it automatically has the word pair in it, but it's not. Para, P-A-R-A, does not mean paired. It means that they are unpaired. That's the thing you gotta know. Para means that you got some unpaired electrons. Dia means you got them all paired up. The word magnetic just describes whether it is going to wind up being magnetic or not. In this example, zinc is diamagnetic because everything got paired. Gallium, however, is paramagnetic because somebody's unpaired. And I will close with this slide, which just gives you the rules. There's a lot of information built into those box diagrams, electron configurations, and it is important to be able to work with them. I will post the video sometime this weekend. It'll probably be Sunday. And I will be in my office from 8 to 4 on Monday.
That's 80, right?
Yes.
Okay. Forgot to put this. Thank you.
This is my advanced one.